Chapter 6, Odd Number Problems 1 through 13. Number 1. A local hardware store has a savings wheel at the checkout. Customers get to spin the wheel, and when the wheel stops, a pointer indicates how much they will save. The wheel can stop in any one of the 50 sections. Of the sections, 10 produce 0% off, 20 sections are for 10% off, 10 sections for 20%, 5 for 30%, 3 for 40%, 1 for 50%, and 1 for 100%. Assuming that all the sections are equally likely, what is the probability that a customer's purchase will be free? So again, we'll begin with the notation. So we are figuring the probability of landing on 100% discount. So 100% of the purchase will be free. So again, given our understanding from Chapter 6, probability can be expressed as the number of outcomes classified as the item that we're interested in this case, 100%, over the total possible outcomes. So again, how many times can 100% occur of the 50? And we find that again, it's 1 of the 50. So 1 over 50, again, the frequency of that particular item over the total number of outcomes. So we simply do our calculation. So 1 over 50 is the same as 0.02. Again, probability is often expressed as a percentage. What is the probability that it will rain tomorrow? It's often expressed as a percentage. So again, this is 0.02, which is the same as saying 2%. So there's a 2% chance that a customer at this hardware store will receive the purchase for free, get 100% discount. Number 1B, what is the probability the customer will get no savings from the wheel? 0% off. So probability of 0% off, again, it's the number of sections that represent 0% off or zero savings. And we find that that occurs, let's see here, 10 times. So 10 produce 0% off. So 10 over the total outcomes is 50. So 10 divided by 50 is 0.20, which is the same as 20%. number 3, what are the 2 requirements that must be satisfied for a random sample? From our reading that we learned that 1, each individual has an equal chance of being selected. Okay. And the reason that researchers use the concept of random sampling is to minimize or ensure that there is no bias in the selection process. So if everyone has a chance, then we aren't biased in the group that we're selecting to represent a sample from the population. And number 2 says that if more than one individual is selected, the probability must stay constant. You can understand this as, again, probability. From chapter 6 we learned that probability of any event can be understood in this format. So the probability of A, event A, whatever it is equal to the number of outcomes classified as A over the total number of possible outcomes. So what we're saying here is that in 2, if more than one individual is selected, the probability must stay constant. In other words, the denominator of this equation must remain constant. It cannot change. So just for example, if I were to have a list of students, let's say I have John and Martha, Sarah, and Maria. Again, we see that we have a sample equal to 5 individuals, and I want to figure out what is the probability that Sarah will be selected, so randomly selected. So again, probability that Sarah will be selected. Again, how many Sarahs are there? Well, there's only one. Over how many students there are that I'm selecting from. So she has 1 out of 5 chances of being selected, 0.2, or 20% chance of being selected. Now, if I select Sarah, if she would happen to be the one that was selected, right, and let's say I take her out, right, I take her out, now we are looking at the probability of n is equal to 4, the sample size, n is equal to 4. So again, probability of Sarah being selected, and we see a problem here. There's a 0 out of 4% chance. There's a 0% chance that Sarah will be selected. So again, in this case, if we don't replace Sarah back into the mix, we are not adhering to the first requirement, which states that each individual has an equal chance of being selected. So if I take her out of the mix, she has a 0 chance of being selected. And as a result, what also happens is that the denominator, the total number of possible outcomes, has decreased by 1. So again, the requirement is that everyone has an equal chance, and that if we do make a selection, more than one selection, that we put back each individual into the pot, into the hat, and allow them an equal opportunity. So you can see that as we replace individuals back into the mix, then we're adhering to the first requirement, which says that everyone has an equal chance. And again, if we put Sarah back into the mix, she again has another chance of being selected. The chances of her being selected twice, obviously, 2 times in a row, decreases and pertains to the multiplication theory of probability, which we won't be talking about in this chapter. But nonetheless, hopefully you see here now what it means to adhere to the two requirements to satisfy implementing random sampling methods. Number 5, we're going to draw a distribution and draw a vertical line through a normal distribution for each of the following z-scores. Determine whether the body is on the right or left side of the line and find the proportion in the body. So we're going to utilize our z distribution or unit normal table to find the proportions that represent the body. So given the video I posted regarding how to use the unit normal table, we should be able to find this information. So our first distribution pertains to a positive z-score. So here's the mean. A positive z-score of 2.50 would be to the right and pretty far out there. So it's 2.5 standard deviation units above the mean. And the body is illustrated by the larger portion of the entire distribution. Okay, so this is the body. And what we're going to do now is go to our unit normal table and find out what is the probability. It's the probability of the distribution that represents essentially any z-score below a positive 2.5. So we want to find out what is the proportion of the entire distribution. The entire distribution represents 1.00 or 100%. And we're going to look for the proportion of this distribution that represents scores below a positive z-score of 2.5. Okay, here's our unit normal table, and I've turned to the page. Again, I'm looking in column A, which is the z-score, for the z-score that was given of 2.5, and I'm going to report the proportion in the body. So again, here we see that proportion, that z-score and the proportion in the body, which is 0.9938. So again, what we've determined that is, given the unit normal table and using a z-score 2.5, the probability of obtaining a z-score less than 2.5 is 0.9938, or there's a 99.38% chance that we would select a score that is equivalent to a z-score of 2.5 or less than that. Okay, so given our unit normal table, we found that the probability is equal to 0.9938. Another way to think of it is that 99.38% of the distribution is represented by z-scores below a positive z-score of 2.5. Next one, we have a z-score, positive z-score of 0.8, which would be pretty close to the mean. It's not even 1 standard deviation unit above the mean, so fairly close. And again, the body is represented by this whole larger area. All of this area between the mean plus 50%. Again, the distribution is symmetrical, so anything below the mean or above the mean represents 50% or a proportion of 0.5. And so we should anticipate that this answer is going to be something close to 0.5 because we're just going up slightly above the mean and less than 1 standard deviation unit. So we're looking for, again, the body, the probability of a z-score less than a positive 0.8 z-score. So let's utilize our unit normal table. Okay, so again, entering the unit normal table using our z-score, we move down until we find a z-score of 0.8, and here we find that along with its proportion, we see 0.7881. So again, we've identified that of the whole, entire distribution represents a proportion 1.00. Obtaining a z-score less than 0.8, positive 0.8, the proportion of the whole entire distribution represented by that parameter is 0.7881, or there's a 78.81% chance that we would select a score that's equivalent to a positive 0.8 z-score or less than that. Okay, so again, given what we found in our unit normal table, we found that the probability is 7.7881. Again, there's a 78.81% chance that we would select a score that's equivalent to a z-score of positive 0.8 or less than that. Again, we wouldn't expect something as large as the first example because that was 2.5 standard deviation units from the mean, and here we're going slightly above the mean and within slightly below 1 standard deviation unit. So we should expect something 50% plus a little bit more, but not significantly more because 0.8 is not very far from the mean. Next one, we have a z-score, there's the mean, of negative 0.5. So again, very close to the mean, 0.5. And again, the body is always going to be 50% or more. So the side of the distribution, unlike the other two, is going to be to the right above that score. Because if we went to the left, that would be less than 50%. So again, this is pertaining to the probability of a z-score greater than a negative 0.50. And just before I forget, I believe that part of this question also asked us to identify the side of the distribution that represents the body. So in the first one, we were talking about the left portion of the distribution that represents the body, similarly with another positive z-score. But in this case, as I just mentioned, it would be to the right because again, this z-score is to the left of the mean. If I went to the left, again, it would be less than 50% or a proportion of 0.5. So it's going to be to the right, which includes half of the distribution above the mean and the area between the mean and a z-score of negative 0.5. So let's go to our unit normal table. Okay, in our unit normal table, again, we utilize column A to find our z-score, and it's here up at the top with the area in the body, or the proportion in the body, which is 0.6915. So let's go back to our problem. Okay, so again, using our unit normal table, we found that the probability of obtaining a z-score greater than negative 0.5 is 0.6915, or there's 69.15% chance that we would select a score that corresponds to a z-score of negative 0.5 or a score greater than that, or a z-score greater than negative 0.5. Finally, the last one, again, we have another z-score that's negative, and again, pretty close to the mean, negative 0.77. And once again, it's a negative z-score, so the body will be to the right of that value. And the probability is equal to, we're going to again utilize a unit normal table. Okay, here is our unit normal table. We enter it using column A to find our z-score of 0.77, and we find it right here, and the proportion in the body is 0.7794. So here we would report 0.7794. So 77.94% of the entire distribution is represented by a z-score of negative 0.77 or above. Or we can say there's a 77.94% chance that we would select a score that corresponds to a z-score of negative 0.77 in this distribution. So again, the purpose of this type of problem, or these types of problems, is just to get us familiar with the location of a z-score and how to utilize the unit normal table given the area of interest, whether it's the body, the tail, the area between the mean and the z. So again, developing those basic skills so that we can take it to the next level of finding the proportion between scores. Number 7, what proportion of a normal distribution is located between each of the following z-score boundaries? So we're going to draw this out. Again, it's essential that you draw your distributions in this chapter and from this point forward, so you get a sense of what you are looking for and you don't make careless mistakes of reporting the incorrect proportion. So again, we're talking about the area between a negative 0.25 z-score and positive 0.25. Again, it's the entirety of this proportion of the normal distribution. So in order to find that, the area that's represented on either side of the mean is referred to as the area between the mean and z-score. Again, we're taking into consideration two areas, one above the mean and one below the mean, but both areas represent the area between the mean and the z. In one case it's a positive z, in the other case it's a negative z. So we're going to find the proportion of one of those areas, and since they're equal distance we can multiply by 2, but first we need to utilize our unit normal table. Okay, using our unit normal table, again, this is the area of interest as it's diagrammed here, which is the column D, so the area between the mean and the z. So I'm going to use column A to find my z-score of 0.25, and here it is, 0.25. And in particular, the area I'm interested in is the area between the mean and the z, which is 0.0987. Now notice that the unit normal table does not contain any negative z-scores, and of course the reason is that the distribution is symmetrical, so the area represented above the mean are identical to the areas represented below the mean. So we don't need to find a negative 0.25. We know that the area between the mean and a negative z-score of 0.25, it would be the equal proportion or equal distance. So to find our final answer, we just would multiply by 2. Let's go back to our distribution sketch. Okay, so again, what we found in our unit normal table is the area, right, that's represented here, which was 0.0987, and recognizing that the distance from the mean to a negative 0.25, so this area, right, would be the same, 0.0987. So again, if we're interested in the area between the negative 0.25 and positive 0.25, we're going to add those two proportions together or multiply by 2. So 0.0987 plus 0.0987, we get the area that's represented by 0.1974. Check to make sure that's all correct. Okay, so again, the proportion of the entire distribution that represents z-scores of negative 0.2 all the way to positive 0.25 is equal to 0.1974. Or 19.74% of the distribution is represented by these z-scores of negative 0.25 to positive 0.25. Okay, so the next one, again, we draw our distribution, and now we're interested in the area between 0.67 negative and positive 0.67. Again, it's the entire area of the distribution that we're interested in. And it's going to be the same process using the area between the mean and the z for the positive and the negative z-score. So again, we're going to look at this proportion, and since it's equal distance, recognize that it also represents this area between the negative z and negative z and the mean. And adding those two proportions together will describe the proportion of the distribution that falls within negative 0.67 z-score and a positive 0.67. I hope I said that correctly. So it's the area between a negative 0.67 z-score and a positive z-score of 0.67. So let's utilize our unit normal table. Again, using the z-score of 0.67, we're going to enter using column A, and we find 0.67 right here. right here, and the area between the mean and the z. So here's our z-score. Area between the mean and z is 0.2486. So the area between a positive z-score 0.67 and the mean, that area between the mean and that positive z-score is equal to 0.2486. That's the proportion. Again, we're interested in the entire area from a negative 0.67 to positive 0.67. So let's go back to our distribution sketch. So again, given what we learned using our unit normal table, this area between the mean and the z, positive z, is 0.2486, and the equal distance on the negative side would be the same proportion of 0.2486. And just a bit of a warning, many students want to report the proportions as negative simply because they're below the mean. But again, the z-score simply tells us the location of the score that pertains to this particular z-score. So it's just telling us where that value is located in relation to the mean. So don't make the mistake of reporting your proportions as negative values. So again, the area that spans between these two values would be calculated by taking those two proportions and adding them together. And if we add them together, we get 4972. Okay, so the area between a negative z-score of 0.67 and 0.67 positive z-score is 0.4972 of the entire distribution, which again represents 1.00, or 49.72% of all scores will fall within negative z-score of 0.67 and positive z-score of 0.67. And finally, the last one. Again, drawing our sketch, we have the z in the middle. Now we're at negative 1.20, further away from the mean, positive 1.20. So again, given the comparison to what we've done thus far, we should expect this proportion to be much larger than the two previous problems because the distance from the mean has increased. So we're going at 1.2 standard deviation units above and below the mean. So we're going to, again, report the proportion between the mean and the z here. Recognize it'll be equal on this side because the distance from the mean is equal. And we're going to use our unit normal table to find this proportion. Okay, so here we are, again, utilizing column A, the z-score of 1.20. We move our way down and we find that value here. Again, the area between the mean and the z is represented in column D, so we get 0.3849. And we'll go back to our sketch and see what it means for this particular problem. So given what we found in our unit normal table, we can express this proportion as 0.3849. 0.3849, and again to identify the proportion of the entire distribution that spans from negative 1.2 z-score to a positive 1.2 z-score, we would simply add these two proportions together. Notice that again, these problems are very basic and we're going equal distance, but we can now apply this skill to any two z-scores, one below the mean and above the mean, using the appropriate column to identify the entire proportion. So if we add these together, we get 0.7698, or what we're saying is 76.98% of the entire distribution falls within a z-score of negative 1.2 and a positive 1.2 z-score. What I neglected to do with the two previous answers, and I'll do that here, is to represent this using the probability statement. So again, for this particular case, we were looking for the probability of scores negative 1.20, right? So scores, a z-score that is greater than that z-score, right? Or a z-score that's less than a positive 1.20. positive. So again, this probability statement is in relation to this shaded area. So again, we're looking for the probability of a z-score, right? That's greater. Here's negative 1.25 here. So greater would be this way, and less than a positive 1.25, so this area. So let's do the same for the other example since I neglected to do so. And I'll find some space here by erasing a little bit of this. Okay, so again, all I want to do is show this as a probability statement. So again, this one was the probability of a z-score that was greater than negative 0.67, negative 0.67, right? So greater than negative 0.67, yet smaller than or less than positive 0.67. Again, expressing this shaded area here. Right, a z-score, the probability of a z-score that's greater than negative 0.67 or a z-score that's less than positive 0.67. And then finally, the first one that we completed, again, it would read as the probability of obtaining, what is the probability of obtaining a z-score, right? That's greater than negative 0.25, yet smaller than positive 0.25. So again, representing the probability statement and then visually interpreting that. So we're looking for a z-score. Again, that is greater than negative 0.25, yet less than positive 0.2. And again, that's that shaded area here. Number 9, we're going to find the z-score location of a vertical line that separates a normal distribution as described in each of the following. So this process is slightly different than what we've been doing thus far. And this is the process of developing a skill that's going to enable us to identify what an X value is that represents the top 5%, the bottom 60%, and other things along those lines. So first what we're going to do is draw our distribution as indicated. So we're going to partition the distribution where 5% in the tail is on the left. So 5%, and I'm just going to write 5% here, which means that 95% is represented in the body. And ultimately what I want to do is find out what z equals here. What is the z-score that partitions the distribution on where 5% is in the tail on the left? Okay, to do so, well, our first step is to convert the 5% into a proportion so we can utilize the unit normal table. So to do that, we would take 5 divided by 100 to get a proportion 0.05. Next, we're going to use our unit normal table to find 0.05 in the tail. I'm going to find 0.05 using the column that pertains to the proportion in the tail, and then report the z-score that corresponds with 5% representing the tail, which also means that there's 95% in the body. So again, I'm looking for 0.05. 0.05. You can think of it as 00 since the proportions are represented or displayed as 4 digits right at the decimal. So I'm looking for the value that's closest to 0.0500, and I'm looking for it in column C, which represents proportion in the tail. So we see here at the top it's 0.0668, and it decreases as we move our way down. Again, our ultimate goal is to report the z-score that corresponds with 0.0500 in the tail. And as we get closer down the page, there are two values of interest here. So we have a value of z-score of 1.64 and z equal to 1.65. So I want you to take note of both of those, and we'll discuss what the difference is. So again, what we see in the area in the tail for 1.64 is the proportion of 0.0505. And for 1.65, the area in the tail is, and again I'm focusing over here, is 0.0495. And again, we want to find the value that's closest to, and given these two values, they're both equal distance from the proportion of interest, which is 0.0500. So because they're equal distance, it would be perfectly fine to report both of those z-scores at this point in our semester or understanding. Again, those correspond to 1.64 and 1.65. And again, notice over here in the area of the proportion in the, let me erase this so I can focus a little bit better, the area in the body, so again 1.64, again notice that we have that 95% in the in the body. So we looked at the area in the tail because that's the area that was identified in the problem. But again, the other corresponding area to make the proportion equal to 1.00 is the remaining 95%. Again, 0.95 would be the area of interest in the body, and we find these two values that are close to it and in fact equal distance. So later on, as we engage in inferential statistics, the z-value of interest would, in the more accurate z-score, would be 1.65, because as we get into conducting hypothesis tests, we are going to focus on finding values that have less than a 5% chance in the tail. So values occurring in the tail that have less than a 5% chance of occurring. So if we were to select z-score 1.4, that's including above 5% chance. But at this point in our semester, if we report both, we're perfectly fine. So again, and the reason we would report both is because they're both equal distance from the proportion that we were looking for utilizing column C. Okay, so now that we found the proportion using the tail and the closest one to it, now that the ultimate goal was to report the z-score. So we found that 1.64 and 1.65 were perfectly fine to report because those proportions in the tail were closest to our 5%. But what I want you to notice is, again, the tail is to the left. So we would recognize that the corresponding z-score would be negative 1.65 or negative 1.65. And again, this is why it's so essential to draw your distribution, identify the location of the value you're looking for, and because this area that's partitioned off by 5% in the tail to the left, that tells us that the z-score is going to be negative. Again, recognizing that the normal unit normal table does not include negative z-score, it's up to us to recognize what side of the mean we're working on. All right, so the next one, we're going to partition off 30% in the tail to the right. 30% to the right. So this would be 30% here in the tail, which leaves 70% in the body. So again, just as we did in the previous example, we're going to convert that 30% to a proportion. So it would be 30 divided by 100, we get 0.3000. And now we're going to utilize the tail of our unit normal table to find that. And our ultimate goal is to identify what the z-score equals here, right? What is the z-score equal that partitions 30% of the distribution, right, to the right and 70% to the left in the body. Okay, so again, I'm looking for the z-score that corresponds to the value in column C, the area of the tail that represents 30%. So I'm looking for 0.33000 in column C, and again, I'm not going to come up with an exact value, but I want to report the value that's closest to. And if you see here, there are two that are relatively close. We have 0.3015 and 0.2981. In the last example, they were equal distance from this ideal value that we were looking for. And in this case, they're both very close, but we recognize that one is closer than the other. And the one that's closer is actually this one. And if you're not completely understanding why I would choose that one versus this one, if we were just to take 0.3000 minus 0.3015, do the subtraction there, and then also 0.3000 subtract 0.2981. The difference, right, between these two will reveal which one is closest. Okay, so if we do the math, over here we get 0.0019, and over here we get 0.0015. And so this is a smaller distance between the value that we were looking for. Again, that was the 0.3000, and what we see in the unit normal table. So again, showing you that we have two values that are close to what we're looking for, but one is closer. And therefore, we would report the z-score that corresponds with that proportion in the tail, and it would be 0.52, because again, that's the value or the proportion that was closest to what we were looking for. That represents 30% in the tail. So let's go back to our distribution sketch. So given what we found in the unit normal table, we would report that this z-score is positive 0.52. So positive 0.52, and I'm just going to rewrite that a little bit so that it's a little clearer. So positive 0.52 is the z-score that represents sectioning off 30% to the right and 70% of the body to the left. Okay, so the next one, we're going to sketch our distribution, and we now are tasked with partitioning the distribution where 65% in the body is to the left. So 65% in the body here, and what left in the tail is 35% in the tail. Again, we're going to convert that 65% into a proportion, so we get 0.65, and we're going to utilize the column that represents the body of the distribution to find out what is z equal to here. What is z equal to here that partitions the distribution off where 35% in the tail to the right, 65% in the body to the left. So let's use our unit normal table to find this. So again, we're using the proportion of 0.6500 in the body. So that's going to be column B. And we're looking for the z-score that corresponds with that proportion in the body. So we move our way down the distribution. We're looking for 0.6500. And we see that these two are closest, 0.6480 and 0.6517. And again, it's a matter of identifying which is closest. And similar to the previous example, we would go with the z-score 0.39 because z is equal to 0.39 because the proportion is closer. Again, our ultimate goal is to find the proportion closest to 0.6500. We have options of 0.6517 and 0.6480. So again, the difference, this one here is going to be different by 0.0020, and this one, the difference is 0.0017. So again, we go with that one which is closest, and that corresponds to z-score of 0.39. So given what we found in our unit normal table, we would report this z-score is 0.39. A z-score of 0.39 partitions the distribution where we have 35% in the tail to the right and 65% of the body to the left. So finally, the last one, we have a distribution where we have 80% in the body to the right. So 80% here, meaning we have 20% in the tail. And again, now we want to find out what is z equal to here that partitions the distribution where 80% is to the right in the body and 20% is to the left in the tail. So as we've done before, 80 divided by 100 to give us the proportion to utilize our unit normal table. And again, this was 0.8000 is what we're looking for, and we're going to utilize the column that represents the body to find this particular answer. So let's go to our unit normal table. Okay, so we're looking for the proportion of 0.8000 in the body. Okay, so we're going to utilize column B, and we're looking for 0.80, and we see here that this is the area that we would focus on, and we find that a z-score equal to 0.84, right, has a proportion in the body of 0.7995. Again, that's the closest value to the value that we were looking for. So again, our z-score would be 0.84. Okay, so using our unit normal table, we've identified that this z-score is 0.84, and again, given the location, right, we're talking about the tail to the left, we know that we must report that as a negative z-score. Again, the unit normal table does not include negative values, which is important to sketch your distribution out. Identify the location of the score you're interested in. If it's below the mean, the corresponding z-score would be a negative value. Number 11, a normal distribution has a mean equal to 70 and a standard deviation equal to 8. For each of the following scores, indicate whether the tail is to the right or left of the score and find the proportion of the distribution located in the tail. So first, the first step is to draw our distribution and label the known values. So we know that in the center we have a score of 70. That's the mean of the distribution. A score of 72 would be to the right of the distribution. And therefore, the tail would also be to the right. So again, the tail is on the right side of the distribution. Next, what we want to find out, what is the proportion of scores above 72? So we could write that probability statement as follows. So the probability of obtaining the score that's let's see here, a score that's greater, again, given the representation of the tail, greater than a score of 72. And I'm going to move all of that down a little bit to give myself room for one more thing I need to do. So again, the probability of obtaining X value that's greater than 72. Okay, so in order for us to solve this, we're going to have to convert that score into z-score. So z is equal to x minus mu over standard deviation. Replace variables. Z is equal to 72 minus 70. Divide by 8. So if we do the math, if we take 72, subtract 70, and divide by 8, we should get a score of 0.25. Again, the z-score simply represents the exact location of the score in relation to the mean expressed in standard deviation units. So again, this is my x distribution. So a z-score for the mean would be 0, and now we're saying that a score of 72 is the same as 0.25 standard deviation units above the mean. So we can actually rewrite this probability statement to say, what is the probability of obtaining the z-score greater than 0.25? And to answer this final question, we're going to utilize the unit normal table and find the z-score 0.25 and report the area in the tail. Okay, so here's our unit normal table. Again, we entered the table using column A, the z-score. The z-score we're looking for is 0.25, and it's there at the top. And the area in the tail is the area of interest. So let's go back and make sense of this in our distribution sketch. So given what we found, this area in the tail is represented by a proportion of 0.4013. Again, we utilize the unit normal table to find our z-score, report the area in the tail, and so we can answer this final probability statement and indicate that the probability of obtaining a score greater than 72 is, there's a 40.13% chance, or the proportion of scores above a score of 72 is 0.4013. or we can read it as a z-score. Again, given that 72 is 0.25 or a quarter of a standard deviation unit above the mean, the probability statement can just be rephrased using z-scores instead of the raw scores. All right, the next one, we have a score of 76, again the mean of 70, score of 76, again to the right of the distribution. The tail is going to be to the right. And now we want to figure out what is the probability of obtaining an x value greater than 76. So to find that out, we have to convert the score into a z-score. Replace values, so z is equal to 76 minus 70, divide by 8, and so if we do the math, again 76 minus 70, divide by 8, and we would find that a score of 76 is 3/4 of a standard deviation unit above the mean. So again, this is my z, this is my x, so 0.75. So we're going to utilize our unit normal table and report the proportion of the distribution above a z-score of positive 0.75, and I'm not sure why I put negative there, but let me erase that. Point, and over here, boy, I sure did mess this one up. So this is 0.75, and this is positive 0.75. I just really made a mess of that. So this is equal to a probability of obtaining a z-score greater than 0.75. Okay, so we're going to use our unit normal table to find that out. Okay, so again, we're going to enter the unit normal table using our z-column. We're looking for a z-score equal to 0.75. And if we move our way down, we find it here. And the proportion of the tail is 0.2266. Okay, so given what we found in our unit normal table, we found that this area is represented by a proportion 0.2266, answering our probability statement. So we can, again, express this a couple different ways. We could say that there's a 22.66% chance that if we randomly selected a score from this distribution, that score would be greater than 76. Or we could say of the entire distribution, 0.2266, that proportion represents scores above 76 or z-scores of 0.75. This is a continuation of 11C. Now we're going to sketch our distribution. Again, the givens, 70 is equal to the mean, and we're considering a score of 66, so that's going to be to the left, 66. And now the tail is on the left. So still, again, our interest lies in the probability of attaining an x value that's less than because it's on the left side of the mean, less than 66. And we're going to convert that 66 into a z-score using our equation. So z is equal to 66 minus 70 over 8, and we get a z-score of negative 0.50. So again, this would be negative 0.50. This would be 0. So we're going to utilize our unit normal table to then answer our probability statement. I'm actually going to move it over here since I have more room to the right. So let's rewrite that. So it's the probability of obtaining an x value that is less than 66, a whole number, 66, which is now the same as the probability of a z value less than negative 0.50. We're going to utilize our unit normal table. So in our unit normal table, again, we're looking for z is equal to 0.50. Again, technically it was negative, but our unit normal table does not have negative values. The equal distance would pertain to a positive z-score of 0.5, and it's here at the top, and we were going to report the area in the tail, the proportion of the tail, which is 0.3085. Okay, so given what we just found in the table, we find that this is represented by 0.3085. right? So the probability of obtaining an x value greater than 66, there's a 30.85% chance, or 0.3085 of the distribution, that proportion of the entire distribution is represented by x values above 66 or z values, below 66 or z values less than negative 0.5. Finally, this last one's very similar. Again, we have our mean in the center of 70, score of 60 to the left, which means the tail will also be on the left. And we're going to find the probability of obtaining an x value less than 60. And to do so, we'll need to calculate our z-scores. So z is equal to x minus mu over standard deviation. Z is equal to 60 minus 70 divided by 8. And we get a z-score equal to 1.25. So again, rewrite the probability pertaining to a z-value. So probability of obtaining a z-value, and this is negative, less than a negative 1.25. Right, so 60 is 1.25 standard deviation units below the mean. We're going to, again, utilize our unit normal table to find the answer. Okay, so here we are. We're looking for z is equal to negative 1.25. Again, noting that there aren't any negative values in our unit normal table. We just used its corresponding positive value, and that's here, 1.25. The area proportion or area in the tail is represented by 1.1056. So let's go back to our sketch. So we found that this area here is representing 0.1056 of the entire distribution. So our final answer would be 0.1056. Again, we can read that as there's a 10.56% chance that if we randomly selected a score from this distribution, that score would be less than 60. Or similarly, there's a 10.56% chance that if we randomly selected a z-score from this distribution, that z-score would be less than negative 1.25. Or 10.56% of the scores are below a score of 60. Okay, last one, number 13. For a normal distribution with a mean of 60 and a standard deviation of 10, find the proportion of the population corresponding to each of the following. So we're going to find, in the first one, we'll draw our sketch, scores greater than 60. So the mean is equal to 60. The score of interest is 65, which is to the right, 65. So we're going to need to, and again, the area of interest that we should shade, find the proportion corresponding to each of the scores greater than 65. That means the tail is the area of interest. Okay, so we're going to find, again, the probability of obtaining an x value greater than 65. And we're going to convert that to a z-score. Z is equal to our score, 65, minus our mean, 60, over standard deviation of 10. 65 minus 60 divided by 10, we get 0.5. And again, this is rewritten as the probability of a z-score greater than 0.5. And we're going to find in our unit normal table that value and report the proportion or area in the tail. Okay, our unit normal table, again, we're looking for z is equal to 0.50, and the area of interest is the tail, because those are the proportion of the distribution greater than that specific z-score. So z of 0.5, area in the tail, proportion of the tail, 0.3085. So what we found in our unit normal table, 0.3085. So the probability of score is greater than 65, or the probability of z-score is greater than 0.5, is represented by a proportion of 0.3085, or we can say there's a 30.85% chance that if we randomly selected an x value, a score in this distribution, that score would be greater than 65. Again, over here, we're just saying the score of 65 is half a standard deviation unit above the mean. All right, next one, scores less than 68, so our mean is in the center of 60, score of 68 to the right, and now we're interested in all of this, the area between the mean and z, and the whole other half of the distribution. So again, given this visual interpretation, we should understand that the proportion we're looking for is definitely going to be greater than 0.5. So the probability of an x value less than 68, we're going to convert our x value into z-score. So the score of 68 minus 60 divided by our standard deviation. So 68 minus the mean of 60 divided by standard deviation of 10, and we get a z-score of 0.80. So this is the same as finding the probability of obtaining a z-score that's less than a positive 0.80 z-score. So we're going to utilize our unit normal table, and again, this is the body. The area of interest is represented by the body of the distribution. Okay, so again, we're looking for a z-score of 0.80. And we find that here, so 0.80, the area in the body is 0.7881. So given what we found in our unit normal table, this is 0.7881, or we would understand that there's a 78.81% chance that if we randomly selected a score, that score would be less than 68, or 0.7881 of the distribution is represented by scores less than 68, or a z-score less than a z-score of 0.8. All right, finally, the last one, we have distribution. We have the mean of 60 in the middle, and we have a score of 50 to the left and a score of 70 to the right. And our interest lies in the proportion of scores between 50 and 70, or the probability of obtaining a score between 50 and 70 in this distribution. So again, our probability statement would read as, what's the probability of obtaining an x value that's greater than 50, yet less than 70. Okay, so I'm going to convert my first score into z-score. So 50 minus 60 divide by 10, and we get -1. And we have z is equal to 70 minus 60 divided by 10, and we get +1. Okay, so we can think of this as -1, +1. Let me go back there. +1. And again, rewriting this, we could say, what is the probability of obtaining a z-score that's greater than -1, or that is less than +1. And this may look familiar to you. Up until now, Graviter from our text has indicated that the approximate value proportion of a normal distribution within one standard deviation unit is equal to 70%. And many of you may be wondering where that 70% came from. Well, now this example is a perfect example to illustrate how we come up with that approximate number of 70%. So again, this area, right, is represented by the area between the mean and the z, as is this one. So we're going to look up a z-score of 1 and report that proportion and double it, because again, we're spanning from a score below the mean and above the mean. Okay, so using our unit normal table, we're looking for a z-score of 1.00, which again would correspond to a negative value of 1.00. Excuse me if I said that incorrectly. The z-score of 1.00, positive or negative. Here is our z-score. Area between the mean and the z is the area of interest, because we're spanning the area above the mean and below the mean. And again, since there are two areas based on our sketch, we're going to add those areas. So we would get 68, 0.6828, again 68.26%. And again, that's where that approximate 70% is coming from. So it's not just made up. we recognize, given the unit normal table, that approximately 70% of any normal distribution will be represented within one standard deviation unit. And here we see how that approximate number has been arrived at. And again, it's taking the area between the mean and the z for a positive one and a negative one, adding those two proportions to come up with the actual value, right, which we often round as an approximate value of 70%. Okay, so given what we just learned, in the unit normal table, this is 0.3413. And this is similar on the other side, 0.3413. Again, don't report it as a negative. The negative just indicates the location above or below the mean. Negative for below the mean, positive for above the mean. And we added those two values and we get 0.6826. Again, we can express that as 68.26% of any normal distribution. Those scores will fall between one standard deviation unit above and one standard deviation unit below the mean.